You are driving along an open highway. There is no sensor connected to your car and no camera following you. Someone simply points a small device in your direction. Seconds later, your speed appears on its display. The device does not use GPS or read your speedometer. It sends an invisible signal toward the vehicle, measures what returns, and converts a tiny change into speed. But there are two very different ways to do this. Radar detects a change in radio frequency. LiDAR tracks how quickly the distance to the vehicle changes. Inside a radar speed gun, a microwave transceiver generates a radio signal at a stable frequency. The antenna directs that signal toward the road, where part of it reflects from a moving vehicle and returns to the device. If the vehicle is stationary, the returning frequency remains almost unchanged. When the vehicle approaches, the reflected wave fronts become compressed, raising their frequency. When it moves away, the waves stretch apart and the frequency falls. This is the Doppler effect. Inside the radar gun, the returning signal is compared with the original transmitted signal. The difference between their frequencies is isolated and sent to the signal processing board. A small frequency shift indicates a low speed. A larger shift indicates faster movement. The processor uses that difference to calculate velocity and display the result, often in a fraction of a second. However, radar does not measure every part of the vehicle's movement. It measures only the speed directed along the radar beam. When the device points almost directly along the vehicle's path, the measurement is close to its actual speed. If the radar is positioned at an angle, it sees only part of that motion. The result will normally be lower than the true speed. This is called cosine error. Radar also faces another problem. Its beam is relatively wide. At longer distances, it may cover several lanes and multiple vehicles at once. A large truck can reflect more energy than a smaller car. A faster vehicle may produce a more noticeable Doppler signal than the surrounding traffic. The electronics can separate some signals by strength or speed, but traditional radar does not create a detailed image showing exactly which vehicle produced each return. That is why the operator must also observe the traffic and identify the vehicle that matches the displayed speed. To target one vehicle more precisely, another device uses a narrow beam of infrared light. A LiDAR speed gun does not rely on the Doppler effect. Instead, it measures distance repeatedly and calculates how quickly that distance changes. When activated, its infrared laser emitter sends a rapid sequence of short light pulses toward the selected vehicle. The pulses are invisible to human eyes. Each pulse travels to the vehicle, reflects from its surface, and returns through the receiving lens. An optical detector captures the weak reflection, while a precision timing module records how long the complete journey took. Because the light travels to the vehicle and back, the processor multiplies the measured time by the speed of light and divides it by 2. This produces the distance to the target, but one distance measurement cannot reveal speed. The LiDAR gun repeats the measurement many times over a very short period. If each new distance becomes smaller, the vehicle is approaching. If the distances increase, it is moving away. The signal processing board compares the change in distance with the time between measurements. Distance divided by time produces the vehicle's speed. LiDAR therefore does not directly see velocity. It creates a rapid sequence of positions and calculates how quickly those positions change. Its beam is much narrower than a typical radar beam, allowing the operator to select one vehicle from a group. The device is commonly aimed at a reflective and stable part of the vehicle, such as the license plate or front lighting area. This narrow beam makes LiDAR especially useful on multi-lane roads. Radar and LiDAR now arrive at the same answer through completely different evidence. Radar listens for a change in frequency. LiDAR watches for a change in distance. So why does the result appear so quickly? Radio waves and infrared light both travel at nearly the speed of light. The device does not spend meaningful time waiting for the signal to cross the road. Instead, it spends that time collecting enough consistent information to confirm the measurement. Radar needs a stable reflected frequency. LiDAR needs a sequence of distances that forms a believable pattern of motion. If the target becomes blocked, the return signal is too weak, the operator moves the device excessively, or the measurements do not agree, the processor may reject the attempt instead of displaying an unreliable result. Weather and surroundings can also affect performance. Heavy rain, fog, dust, or road spray can weaken and scatter LiDAR pulses. Radar can receive unwanted reflections from signs, large roadside objects, or several vehicles inside its beam. Poor aiming can make either system less reliable, while an excessive angle can cause the measured speed to fall below the vehicle's actual speed. This is why the device does more than search for a number. It looks for a consistent chain of evidence proving that a real target is moving at that velocity. What appears to be one simple trigger pull is actually a rapid engineering process. A signal is generated and directed toward the road. A vehicle reflects a tiny portion of it back. Sensitive electronics isolate the return from surrounding noise. The processor analyzes either its frequency or its travel time, verifies the data, and converts it into the speed shown on the display. Radar detects motion hidden inside a reflected radio wave. LiDAR measures motion through a stream of invisible light pulses, and before the driver realizes the device has been aimed at the vehicle, the signal has already reached the car, returned to the receiver, passed through the processor, and become a number on the screen.